Welcome to the Chidon's Academy UNN, where we offer proficient learning solutions that will help you to understand appropriately and be able to go ahead and work with the knowledge that you have gained. I am David Ede, and today we are going to be looking at stereochemistry, which is going to cover the aspect of optical activity and its relationship with drugs. The first aspect we're going to be looking at is optical activity and chirality. But before we go further, we have to understand exactly why we have to be talking about optical activity as it relates to drugs. Now, the issue of optical activity is going to be taught appropriately. So just follow me carefully while we make progress in this particular lecture. So the first thing I'm going to be highlighting is the incidents that occurred some years ago, which happens to be that of thalidomide. Now, when thalidomide was initially introduced, it was introduced as a wonder drug because of its sedative effect. Now, that sedative effect is usually used on pregnant women to treat morning sickness. But then it was realized over time that children that were given birth to by those women had some defects, and that we refer to as teratogenic effects. So those teratogenic effects happens to be teratogenic simply means that the embryonic development of the child was interfered or interrupted. So there are other agents that actually can cause teratogenic effect, like alcohol, like X-ray, but thalidomide happens to be one of them. Thalidomide happens to have two mirror images that are non-superimposable on each other. What do I mean by non-superimposable on each other? If you look at a structure like this, this is hydrogen, this is hydrogen, this is hydrogen, this is hydrogen, and then you put something that looks like a mirror here to mirror this particular image. You're going to be seeing this also on this side. So this hydrogen is this hydrogen, this hydrogen is this hydrogen, this hydrogen is this hydrogen, and this hydrogen is this hydrogen. If you take this compound and put on this compound, they are both superimposable because they are having the same things around the different four bonds. But then that is not the case for thalidomide. Thalidomide mirror images do not superimpose on themselves. You understand better as we make progress. So it was later realized that the S enantiomer, which I'm going to be explaining, was actually responsible for the teratogenic effect of thalidomide, while the arrow enantiomer is what is responsible for the sedative effect that is necessary for the treatment of morning sickness in pregnant women. So before we make progress, we are going to be looking at isomerism. Now, from isomerism, we can now make progress to the aspect that concerns us, which is stereochemistry, stereoisomerism, and then moving down to the optical aspects of it. So let's make progress. What are isomers? Isomers happens to be compounds that have the same molecular formula, but then they have different arrangements. Those are isomers. Isomers refers to compounds that have same molecular formula, but they have different arrangements. Now, isomers happens to be divided or categorized into different groups. So isomers are divided into different categories. Like I already mentioned, isomers refers to compounds that have same molecular formula, but they have different arrangements. So basically, isomers are divided into two categories. We have the constitutional isomers, also referred to as structural isomers, and then we have the stereoisomers. So we have the stereoisomers. Now, what do we refer to as constitutional structural isomers? As you've already seen from the name structure, these particular compounds, they have same molecular formula, but their difference is captured in their structure. Now, constitutional isomers or structural isomers happen to be of three different types. Now, we have the chain, we have the positional, and then we have the functional. So our focus today is actually on the stereoisomers, but for the sake of understanding, I'm going to explain this clearly before we move over to the stereoisomers. So what do we refer to as chain isomerisms under constitutional, also known as structural isomers? Now, in chain isomerism, what we are concerned about is the fact that the difference between the two compounds happen to be that in the structure of their carbon chain. Carbon chain refers to the connections of the carbons in the organic compound. And for you to understand appropriately, I'm going to be giving a very good example. For example, a compound that has the molecular formula C4H10. C4H10 happens to be a molecular formula for a compound, but then we are going to draw out two compounds that have this same molecular formula, and then you see what I meant by chain isomerism being a function of the difference in the structure of the carbon chain. So when we have carbon linked to carbon, linked to carbon, linked to carbon, we are having 4 carbons there, which is corresponding to this. Then we have hydrogens that are attached to these particular bonds. So this is hydrogen 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now this happens to be butane, which is the 4th member of the alkane family. It has this molecular formula, but then I want to draw another structure that has this same molecular formula. Now here is the second structure. We have carbon linked to carbon, linked to carbon, and then we have another carbon here. Now I'm going to be attaching the hydrogen. This is hydrogen, this is hydrogen, this is hydrogen, hydrogen, hydrogen with a bond, and then hydrogen with a bond, hydrogen with a bond here. Then we have hydrogen, we have hydrogen, and we have hydrogen. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 hydrogen, and how many carbons do we have? We have 1, 2, 3, 4. So it also has the same molecular formula, but what's the difference? The structure of the carbon chain. Here we have a straight chain carbon of butane, and then we are having here a branch chain carbon arrangement. And this particular compound, for us to name it, you have to look at the longest chain here. You can either decide to go this way or go down this way, but it's 3 carbon. That's what makes up the longest chain. So this happens to be a propane, but then we have a methyl group attached to carbon number 2, because we can decide to number from here 1, 2, 3, or we can number from here 1, 2, 3, or choose anywhere we want to go, but you also realize that this is the carbon number 2. So this particular compound is 2-methyl propane. Meanwhile, this particular compound happens to be butane, or you can call that your N-butane. So butane and 2-methyl propane happens to be chain isomers. I hope you are getting me very clearly. So the next one I'm going to be talking about is the positional isomerism. Alright, so positional isomerism happens to deal with functional groups that are in a compound, but then they are in different positions. So when you have compounds that have same molecular formula, but the arrangement of their functional groups is just different in different positions, then what we have there refers to positional isomerism. I'm going to be giving a very good example in this particular lecture guide. So let's look at this now. We have 1, 2, 3 carbon atom, and then we have hydrogen, we have hydrogen, we have chlorine here, we have hydrogen, we have hydrogen, we have hydrogen, we have hydrogen, and then we have hydrogen. So this compound happens to be 1, 2, 3, that's 3 carbon. Then the hydrogen is 1, 2, 3, 4, 5, 6, 7 hydrogen, and then we have 1 chlorine atom. Now what we call this, based on the position of the Cl, we refer to this because it's on the carbon number 1, this is carbon number 2, this is number 3. We have to start from here because of the presence of the chlorine atom. So this happens to be 1 chloropropane. This is 1 chloropropane. Now let me draw the positional isomerism for this particular compound so I can illustrate it. Now we can also have a compound that is this way and also having 7 hydrogens, but then the difference between the two of them happens to be the presence of the chloride atom on the carbon number 2. So we have 1, 2, 3. So this particular arrangement is going to refer to as 2 chloro, 2-chloropropane. Now, two of them have the same molecular formula C3, H7, and Cl, but the positions of the functional group is different. Here we have it on carbon number 1, while here we have it on carbon number 2. So that is that about positional isomerism. So the next one we'll look at under constitutional structural isomers refers to functional isomers. Now, functional isomers happen to be isomers that occur with different functional groups but same molecular formula. You're going to be seeing what I'm talking about the moment I work on this particular structure. Now we have this. We have this, and this compound has 2 carbon, C2, it has 5 hydrogen, H5, and then it has an OH group. This happens to be an ethanol. This is ethanol. I don't know if you're getting me. This is ethanol. This is 1, 2. That refers to the 8. Then we have the OH group, which refers to the alcohol or the alcoholic group. So this compound is ethanol. But then we can also have another compound that has this particular molecular formula but a different functional group, and let's look at that particular compound. So we have C. Okay, we have C. Let's do it this way. All right, so let's look at this very carefully. Now this is okay. I can actually, this compound, because we have hydrogen and high hydrogen here, we can also write this as C2H6O as the appropriate molecular formula. So we can also count this and see how many carbons and how many hydrogen we have here. We have 1, 2, that's 2 carbon. We have 1, 2, 3, 4, 5, 6. We have 6 hydrogen, and then we have 1 oxygen. This happens to be an ether, and we call it methoxymethane because we are having a met group here. We also have a methyl group here, methyl. So this is methoxymethane. The old name for this happens to be dimethyl ether, so showing the functional group which it belongs to. So we're going to be progressing to the main deal of the day, which happens to be stereoisomers. So stereoisomers, what are stereoisomers? Stereoisomers refers to isomers that have the same molecular formula, have the same structural arrangements, but they have different configurations in space. They have the same molecular formula, same structures, but then they have different configurations or different arrangements in space. That's spatial arrangement or spatial configuration. And for stereoisomers, we happen to have 2 types of stereoisomers. Now, stereoisomers happen to be divided into 2. We have 2 types of stereoisomers. So we have the configurational stereoisomers, and then we have the conformational stereoisomers. So but the configurational isomers happen to also be divided into 2 categories, and the configurational isomers, we have the geometric isomers, and then we have the optical isomers. All of these things you are going to be understanding them as the lecture progresses because they are quite deep. So you're going to be understanding it as the lecture progresses. So the optical isomers happen to also be divided into 2. So the optical isomers, we have diastereomers. Okay, I think I made a mistake. This is diastereomers, and then we have enantiomers. So this is like the category of isomers that we have. So under stereoisomers, we have configurational, we have conformational, we have geometric, we have optical. Another optical, we have diastereomers and enantiomers. So as we make progress in this particular lecture, you are going to be understanding these different isomers that are under stereoisomers, which is the basis on which you are studying stereochemistry and optical activity with regards to drug molecules. So the next focus we are going to be focusing on happens to be with regards to polarized light. Now, it is very, very important for us to study polarized light because polarized light is actually what we're going to use to understand optical activity. So, what do we mean by polarized light? Polarized light happens to be a light that vibrates in only one plane. A light that vibrates in only one plane. Now, if you look at sunlight or the light that comes from your electric bulb, you will realize that the light vibrates in different planes that are perpendicular to the direction of propagation. So, for example, let me just draw something very clearly that is going to help you understand it. So, let me assume that this is a bulb. Let me assume that this is a bulb. Now you realize that light that travel through this bulb travel on different planes. The light travels in different planes. So this is what we're having here. So the light is traveling in different planes. This is typical of your bulb light, your sunlight, and all of that. So, but when we're working with optical active materials, we have to provide lights that travel in one plane. And one way to do that is by using a device referred to as polarizer. So I'm going to be drawing a sketch picture of something that is going to represent our polarizer here. So this is like our polarizer in this place. What is the polarizer going to do? The polarizer will make only one vibration. That's a light that is vibrating in only one plane to get across to it. So with this polarizer, instead of having these multiple directions of vibrations crossing this particular part, we'll have just a single vibration on one plane crossing through. So that's what we refer to as this is what we refer to as polarized light. So this is the light source, this is the light source, and this is our polarizer, and then this is our polarized light. And it's very important, I have to let you know that the light we're talking about here is the linearly polarized light. Now, why do I have to highlight linearly polarized light? Is because lights can be polarized circularly and lights can also be polarized elliptically. So, but for the purpose of this particular tutorial, our focus is on linearly polarized light. Let me talk a little bit about polarizers before making progress. Now, polarizers happens to be equipments that or substances that you use to make light travel or vibrate in one plane. That is what we refer to as polarizers. And for polarizers, we have different kind of polarizers, and we have two basic types of polarizers. We have two basic types of polarizers. We have the absorptive polarizers, and we have the beam splitting polarizers. Now, these absorptive polarizers we're talking about, these ones are responsible. The way they operate, how they operate is that every other light that is vibrating in other plane is absorbed by the material, while the light that they want to cross through on one plane is the one that goes past the polarizer. So it works by absorbing unwanted signals of vibrating lights, and then the one that is necessary is what passes through it. But the beam splitting polarizer actually operates by splitting the light rays and making sure that the kind of light or the vibration of the light that you need to pass across is what passes across the particular material. And for knowledge purpose, it will interest you to know that we have an example of absorptive polarizer happens to be the Polaroid. Now, the Polaroid is made up of PVA. What is PVA? PVA is polyvinyl alcohol that has an iodine doping. So this is an example of an absorptive polarizer. While for the beam splitting polarizer, we have nickel. We have nickel prism. Now, nickel prism happens to be made of calcite, and calcite happens to be a type of calcium carbonate. Calcium carbonate, that is CaCO3. So its operation is by beam splitting. So outside these polarizers, we have polarizers that lead to circular polarization of light, and we have those that lead to elliptical polarization of light. So we have linearly polarized light, we have circularly polarized light, and we have elliptically polarized light. So when you want to work with circularly polarized light, you have to deal with the quarter wave plates. So, but like I mentioned in this particular lecture guide, our focus is on linearly polarized light, hence the focus on these types of polarizers. So let's make progress and begin to talk about optical activity. So I'm going to be talking about optical activity, which relates to molecules or compounds that are capable of rotating lights. So one of the instruments that is being used to study the rotation of lights by different compounds is polarimeter. Now the polarimeter, let me highlight the important parts of the polarimeter so you understand how it operates and how it relates to optical activity of molecules. Now we have the light source, we have the light source, they have the this now we refer to this as lenses. You can refer to them as lenses, but they are polarizers. So the first one serve as a polarizer, but then, like I said, these two, you can refer to them as two lenses. So, but then these are also polarizers. So, but the first one will serve as a polarizer. The one we are working with here, this one refers to as the sample tube. Now, the sample tube is where you put the sample that you want to understand the degree of rotation that is observed when polarized light passes through it. Then this second polarizer is referred to as analyzer. And then we have the human eye viewing it to check the angle or the degree of rotation. So now let's understand how this operates. Now this is a light source, and then it produces light that vibrates in different planes. So but when it passes through the first lens, which is a polarizer, and it can be called prism, or it can also be the other type of polarizer we talked about. So it now produces a plane polarized light, as you can see here. Now, the sample that I want to analyze is already inside of this place, and usually measurement of optical activity is done on fluids, which fluids consist of liquids and gas, and it's usually with regards to aqueous solutions. So, but there are some crystals that I can also study their optical activity, but mainly we study optical activities of fluids, which are liquids and gases. So, but most of them are aqueous solutions. It's already dropped inside the sample tube. Now, standard tube for polarimeter has a path length of 1 decimeter, and from normal mathematical relationship we know that 1 decimeter is equivalent or equal to 10 centimeters. So that's for standard polarimeter tube. So when it passes through the sample, if the sample is optically active, it will rotate the light. If the sample is optically active, it will rotate the light. So when it rotates the light, you can already see that the light is no longer the way it is now in a rotated format. You now use the next polarizer, which is now serving as an analyzer now, to be able to dictate the degree of the rotation, to look at the observed rotation of this particular light caused by the sample in the tube, and we refer to that as our alpha. And then with that, you can be able to analyze the different enantiomers of compounds and know the degree to which they rotate plane polarized light. So let's see how that can now apply in calculations, because basically compounds that exhibit this optical activity, they have mirror images that we refer to as enantiomers. Enantiomers, as we already saw, is a type of optical isomers, which is under configurational isomers, which is under stereoisomers, which is under the broad heading of isomers. So enantiomers refers to compounds that their mirror images are not superimposable. Their mirror images are not superimposable. For us to understand this very, very clearly, let me draw this structure and let us run with it. Now, this structure we have here happens to be a structure of propanoic acid. We have 3 carbons, and then we have a carboxylic acid group here. So this is propanoic acid. Now, if we run a mirror, on this, and then you get the mirror image of this, you're also going to be having a compound that goes this way. Now, this is the mirror image of propanoic acid. But then, So that you understand basically what we're having here, we have different kind of bonds that are captured in this place. We have the stick bond. These ones are plain, they are on this particular plane. And then we have the wedge bond, which is actually representing bonds that are coming out from this plane. And we have the hash bond, which represent bonds that are going away from this particular plane. So we're looking at this as a plane, and then we are using this now as the one to represent the bonds coming out, and this as to represent the bonds that are going backwards. What is the implication of this? It shows you that every of this molecule is not on the same plane. Every of these molecules are not on the same plane. We have those that are on this plane, which is represented by a stick bond. Then we have those that are going this way and the other going the other way, which are represented by the wedge bond and the hash bond. Now, the wedge bond happens to also be referred to as beta bond. Wedge bond also referred to as beta bond, while the hash bond also referred to as alpha bond. So it's very important to take note of those. Now, when we put a mirror here, you have a mirror image of the propanolic acid. You realize that what's changed? The only thing that changed is that the hydrogen that was at the front is now at the back, and the hydrogen that was at the back is now at the front. Now, you may look at this and be like, but these two hydrogens are still at the back. This is also this. Now, can we be able to redraw the structure so you understand clearly what has taken place at this particular point? So for us to look at this now, so it will appear the way this one appears, in this mirror image format, what we just simply need to do is to flip this thing by 180 degrees. So it will still remain on this plane, but then it's going to appear in this format. So let's flip it by 180 degrees. Now, the rule is, if you are flipping it by 180 degrees, the moment you flip it, you have to do one of two things. You either decide to change the substituents that are on the different bonds, or you change the bonds that are attached to the substituents. So let me draw this appropriately. So we are rotating it 180 degrees. So we're going to have this. We're going to have this. This is carbon, and then we're going to be having our hash bond, and we're going to be having our wedge bond. Now, like what did I say? I said that we're going to either decide to change the bonding attached to this, or change the substituents. Now, you can already see from propanolic acid that we have the same substituents. So whether you put hydrogen here and you put hydrogen here, or you decide to take this hydrogen and put it here, and take the other hydrogen and put it here, you still have the same compound. Now, let me ask you a question. This compound and this compound, are they not the same? They're exactly the same compound, and if you put this on this compound, it matches. That's what I refer to as superimposable. It is superimposable on its mirror image. But there are some compounds that are not superimposable. Those are the ones that have this optical activity. Now, for you to be able to understand that, let me draw the structure of lactic acid. So what we have here is still the structure of propanolic acid, but the moment you have a substituent of a hydroxy group here, OH, what you're having here is a lactic acid molecule, a lactic acid structure. Now, you're already seeing now that what we have here, we have H on this part and we have OH on this particular aspect. The moment you have the mirror image, you have OH here. You have OH here. You can also write as HO because it's directly connected to the oxygen, which now links to the hydrogen. Now, how do we make this to look like this and such that it will still be representing a mirror image? Like I said before, first thing first, we flip by 180 degrees. The moment you flip by 180 degrees, the next thing you do is one of two things. It's either you put the substituents and change the bond, or you leave the bonds the way they are and change the substituents. Now, in this particular case, I'm going to change the substituents. I'm going to leave the bonds the way they are. So the HO, that's the hydroxy group, will now be on this particular bond because it was on wedge here. Now it is now on the hash or the dash bond, and then the hydrogen that was on the hash or dash bond is now present on the wedge bond. Now look at this very closely. This image is the mirror image of this, but cannot superimpose on this, because while hydrogen is going backwards and OH is coming out, in this particular mirror image, the OH is going backward and the hydrogen is coming out. So what we have here in lactic acid has optical activity. So we can say for sure now that lactic acid mirror images is not superimposable on itself. So the mirror image of lactic acid is not superimposable on the original molecule, and that is the basis for optical activity. So this kind of molecule will definitely lead to rotation of light, and then the degree to which it rotates light is a unique characteristic for each of those particular compounds. So we're going to be looking very quickly at some calculations that has to do with observed rotation, specific rotations, and how concentration of the molecule in the or the compound in the sample tube and the path length of the sample tube contributes to the degree to which rotation occurs in the polarimeter. So we're going to be looking at some calculations in optical activity to understand how to calculate for the observed rotations that you find after passing plain polarized light through a sample that is optically active. Now take note of this. We have what's called specific rotation. Now specific rotation is denoted by alpha in brackets, and then we have T over D, or we can also write it as alpha in brackets and then we just put D. Now let me explain what this refers to. Now alpha, this symbol represents specific rotation. Now specific rotation refers to the rotation that is specific for every molecule. Just like every compound has their melting point, has their refractive index, has their boiling point, and so on and so forth, specific rotation is a unique property of every particular chemical compound that expresses optical activity when you pass polarized light through it. So specific optical rotation is usually measured when you are using a sodium light. Now sodium lamp light has a wavelength of 589 nanometers. A wavelength of 589 nanometers. Now it is that wavelength that this sodium lamp that is represented by the D. The sodium lamp is represented by a D. Now the T happens to be the normal room temperature, used for such measurements, and usually what we have there is 20 degrees Celsius. That's what we have. So if you measure the specific rotation of a compound using sodium lamp and the temperature at 20 degrees, and another important thing again, with a standard polarimeter sample tube, like I told you, the polarimeter sample tube, the length of the tube is also referred to as path length. It's also referred to as path length, and the path length we are having here, we can denote it as L. And for a standard polarimeter tube, what we have is 1 decimeter. And then the concentration of the molecule, because the amount of the molecule is going to influence what you are having from this particular result. So when you have a concentration, now you can call it concentration or you can call it density. You can call it concentration or you can call it density. Now, when do you call it concentration? You call it concentration when it's a solution. When do you call it density? You call it density when it is a pure liquid. Take note of that. When it's a solution of like a solute and then a solvent, you work with concentration. But when it is a pure liquid and there's nothing dissolved in it, you work with density. When you have such of 1 gram per mil. So when you carry out the measurement for that compound with a sodium lamp of 589 nanometers and a temperature of about 20 degrees Celsius with a path length for the sample tube of 1 dm, and that's decimeter, and then a concentration or a density of 1 gram per mil, the degree of rotation you're going to have, or the angle of rotation you're going to have, is the specific optical rotation. So but then we are aware that different factors can lead to the different changes of the concentrations. So there's an equation that has been derived for it to be able to relate observed rotation to specific rotation. So I'm going to be writing that equation out. So we have that our specific rotation, our observed rotation is equal to specific rotation times path length times concentration. That is if it's an aqueous solution. Or we have observed optical rotation and then specific optical rotation times path length times D when it is a pure liquid. Solutions and then pure liquids. Solutions and then pure liquids. And then from this particular relationship, we can actually be able to calculate the specific rotation. So we have specific rotation, making it a subject of formula. Specific rotation is now equal to the observed rotation divided by the path length times either your concentration or your density. So that now makes us or gives us an idea of what the unit of specific rotation will be like. Now, this is measured in degrees. So we write degrees. That's the unit of specific rotation. That's what we're trying to talk about now. This is measured in degrees. So we write degrees. Now, this happens to be decimeter, dm. So we can write this as per dm, and then the concentration or the density is in gram per mil. So it's going to be mil minus 1, and then we have mil, and then we have gram minus 1, because the mil is already at minus 1, and then when you invert it, you just have your mil, and then you have per gram. You can also represent the unit as degree per dm per cm cube. Now, cm cube actually happens to be another unit for the mil. It's equivalent to mil. And then we have g minus 1. Now, if you convert your dm to cm, you can also have degree. You have cm minus 1. You can use your cm cube, or you can use your mil, and then gram minus 1. This is the one we usually find being used commonly, but any one of them can be used as a unit for specific rotation. So that is that about specific rotation. Now, one very important thing you have to take note of here is that when concentration is usually given, sometimes they give concentration in gram per 100 mil. They give concentration in gram per 100 mil. This refers to as percentage weight volume. And then when you have your concentration in gram per 100 mil, what do you do about your formula? Very simple. What you simply do is that you multiply the numerator using 100. So what we have is specific rotation is now equal to observed rotation times 100 over path length times concentration, and with that you are taking care of the concentration I was given in gram per mil. Now, it's also very important to take note of the fact that sometimes when you are giving concentration, you may not be giving any units for the concentration. According to scientists, what is being said is that when you find a concentration that doesn't have any units, you should assume that the concentration is in gram per 100 mil, and with that in mind, you can go to proceed with your calculations. Now, let me talk about the enantiomers. Now, seeing that each of these enantiomers can rotate light to different degrees, now one rotates it to the right, another one rotates to the left. Now, let me explain what names are usually given to such rotations. Alright, so we're going to be looking at the enantiomers, and then let me explain something very clearly. Now, when the substance rotates lights to the right, we refer to such enantiomer as dextrorotatory. And this dextrorotatory can be represented as D or by a plus sign. So you can use D and you can also use plus. And then when it rotates it to the left, this is for right, please. This is for right. Now, when it rotates it to the left, what we call that is levorotatory. So what we have is L, and you can also designate that as your negative. So that's what we used to refer to as optical activities of drug. So if you see something like this, lactic acid, it simply means that this enantiomer of lactic acid is responsible for the rotation of the polarized light to the left. While when you have the plus or D lactic acid, it means that the lactic acid we're talking about is the enantiomer that rotates lights, plain polarized lights, to the right. So it's very important you take note of that. Another thing you have to take note of is that this enantiomers rotate light to the same degrees, just that the difference is in their direction. So if lactic acid, for example, an assumption, rotates lights, for example, to, let's say, this one rotates to minus 23 degrees. The one that is dextrorotatory is going to rotate lights to plus 23 degrees. Do you understand that now? Now, on this particular basis, it simply means that if you have these two in a particular solution in equal concentration, as this one is rotating to minus 23, the other one is rotating to plus 23, and the implication is that you're going to have 23 plus 23 minus 23, and that's going to give us 0 degrees. So you're not going to have any rotation. So the implication is that you can have an optically active molecule in a solution, but it is not going to rotate plain polarized light because you have the two enantiomers at equal concentrations. Now, such type of mixture is referred to as racemic mixtures. Such type of mixtures are referred to as racemic mixtures. So what you're having here is not the property of the dextro rotatory, it's not the property of the level rotatory, it's a combination of the two properties. And racemic mixtures can go ahead and begin to exhibit different characteristics that are different from the level and also from the dextro. And in a polarimeter, they will not produce any form of optical rotation that can be observed, not because we don't have enantiomers there, but because we have enantiomers that are at equal concentration. Now, what do we mean by the term enantiometric SS? Now, enantiometric SS refers to a mixture that contains two of the enantiomers, but one of them is in SS. The implication is that that one decides the degree of the rotation that is going to be observed when it is placed in a polarimeter. So even if two of them are present, when you have one more in SS than the other, it is going to determine the observed rotation from the particular molecule. For example, let me assume I have a racemic mixture that have an observed rotation of, let's say, plus 10 degrees. What it simply means is that you have both the dextro rotatory and the level rotatory in this particular racemic mixture, but because of the plus sign, it means that the dextro rotatory is more in concentration than the level rotatory. So enantiometric SS, like I already mentioned, is what's responsible for, like when you have one excess of one enantiomer responsible for the optical rotation. For example, let me assume that in a molecule you have the dextro aspect, you have it as 65% of the racemic of the mixture, and then for the negative, that's the level rotatory, you have it as 35% of the mixture. That makes up 100%. The implication is that what you're going to have it now for the percentage that is that is the enantiometric SS here is now going to be 65% minus 35%. Now, when you do that appropriately, it's going to be what? 30%. The implication is that the extra 30% of the dextro rotatory isomer, or dextro rotatory isomer that has the positive sign that's rotating to the right, is what's going to be responsible for the observed rotation of the mixture. So now let's look at some equations that are necessary for calculating the enantiometric SS before we proceed to some examples that will help us understand how to calculate specific rotation, observed rotation, and then the observed rotation for the mixture that we have here. So the specific rotation for the mixture of the two enantiomers is equal to the observed rotation divided by the path length times concentration. Now, if you want to calculate the percentage enantiometric SS, what you simply do is that the percentage enantiometric SS is equal to the percentage of the dextro isomer minus the percentage of the level isomer. So depending on which of them is SS, that's what's going to give you the percentage of enantiometric SS. Then another calculation again we can want to run here is how to now calculate for percentage enantiometric SS using these particular factors. So we have that the percentage enantiometric SS is now equal to the alpha specific mix of the mixture divided by the specific optical rotation of one of the enantiomers, one of the pure enantiomers, times 100. So the Enantiometric essence for one of the pure enantiomers is the specific rotation we're having for it, the rotation of the mixture, and then the specific rotation for that particular isomer multiplied by 100 we get the enantiometric SS.